probability. I'm assuming you guys have seen probability stuff before. I'm going to go through this vocab. Hopefully this is familiar to you. So the first thing that we're going to talk about is the outcome. The outcome is the result of a trial. So the result of a single trial is an outcome. So for example, if we flip a coin and we flip heads, that's the result of one coin flip. The sample space represents all the possible outcomes of a coin flip or some kind of event happening. For a coin flip specifically, the two potential outcomes in the sample space are heads or tails. An event is something that we are going to use for our predictions. So an event is any outcome or group of outcomes. So for example, an event that we might choose to test is what is the probability that we flip two coins and they both flip heads. So two coins flip heads. Could be an event. And then we are going to find the probability that that event occurs. So probability of an event, we use this notation here where we use that capital P and then in parentheses we name the event. It tells us the likelihood that that event occurs. So for another example, what is the probability that we flip a coin and it lands on tails? Okay, we have two different kinds of probability that we're going to talk about. The first is theoretical probability. This is like in an ideal world, everything goes according to plan. What is the theoretical probability that something happens? So to calculate this, we have a little bit of a formula. It's where we take the number of favorable outcomes, so the outcome we want to happen or the outcome that we are testing, over the total number of possible outcomes. So favorable over possible. So for example, if I wanted to find, let's keep going with this same example, the probability that I flip tails, well, how many possibilities are there? I know that there's two. How many of them are the one that we want? We only want tails, so one of them is the one we want. So the probability of flipping tails is 1/2. Good? Kind of in that same vein, we have something called a complement. A complement is the probability that something does not happen. So the probability of not flipping tails, the probability of not tails, would be like 1 minus the probability of flipping tails, which is 1/2. Which we know this is an easy one. There's only one other outcome. So the probability of not flipping tails is 1/2. But we do need to know this little formula right here. 1 minus the probability that the event does happen gives me the probability that the event does not happen. Any questions on that one? And then the last one that we're going to talk about on the next page is experimental probability. And this is similar to the theoretical probability where we're doing favorable outcomes over possible outcomes. But instead of just like the total number of favorable outcomes here, we're actually going to test the event. Okay, we actually do some kind of experiment or test where we can calculate the exact number of times that the event occurs and then the number of times that we did the experiment in total. So for example, let's say that we're flipping a coin. Let's pick a random number. Let's say I flipped this coin 62 times. And let's say out of those 62 times, I ended up flipping heads 37 times. So the experimental probability of me flipping heads in a coin flip is 37 out of 62 times, which isn't exactly 1/2 like our theoretical probability would state it should be. Okay? Experimental probability and theoretical probability are not always the same. Does that make sense? Okay. I'm going to need a little bit of help here. Hopefully we know what a die looks like, right? There's 6 sides on a die. So let's talk about the probability of all of these different events. So this first one, the probability that we roll a 2. We're going to set up this fraction. The total number of outcomes goes on the bottom. How many total choices are there? There's 6. How many of them are 2? Just one of them. So our probability that we roll a 2 is 1/6. What about the probability that we roll an even number? 3 out of those numbers are even, 2, 4, and 6, and there are 6 total numbers. We're going to reduce that to 1/2. What about the probability that we roll an odd number? Same thing, 3 out of 6. The odd numbers are 1, 3, and 5. There's 3 of them out of 6 total on the die, so that's 1/2 probability as well. Okay, let's make it a little bit more complicated. What's the probability that we roll greater than a 4? Can we make it out of 6 first? 2, 6. There's only 2 outcomes greater than 4. It's 5 or 6. So that does reduce to 1/3. What about the probability that we roll less than or equal to 3? Less than or equal. 1, 2, or 3. Those are my only 3 options. So that's 1/2. What's the probability that we roll a 7? 0. I cannot roll a 7. So 0 out of 6 is 0. And then what's the probability? Oh, I'm missing a P in front of here. What's the probability that I roll either an even or an odd number? 100%. 6 out of 6 times I will either roll an even or an odd number. Any questions on that? Fantastic. All right. Whoops. In a taste test, 50 participants are randomly given a beverage to sample. There are 20 samples of drink A, 10 samples of drink B, 10 samples of drink C, and 10 samples of drink D. What is the probability that a participant does not get drink A? Okay, this is our idea of a complement. Is everybody paying attention? Yes. If I say what's the probability of something not happening, I'm referring to the complement. To find the complement, we have a formula. It's right up here. We take 1 minus the event happening in order to find the probability of it not happening. So I'm going to write that out. The probability that it is not A is equal to 1 minus the probability that it is A. So what is the probability that it is drink A? How many total beverages are there? How many total beverages? There's 50 total beverages. How many of them are drink A? So then 1 minus 20 over 50 is what? Let's reduce that to 3/5.
You simplified it from the 20 out of 50.
You could have, yes. Any questions on that? Compliments. Okay, flip it over. How well do you guys know a deck of cards? Are we familiar?
Yeah.
Okay.
There's like 52, right?
There are 52 cards. Out of those, how many suits? 4 suits. How many colors?
2.
There's 2 colors. And if I'm looking at just one suit, how many face cards are in a suit?
3.
There's 3 face cards in a suit. Okay. Ready? What's the probability? You can simplify this down in your head. What's the probability that we pull a card and it is not a spade?
48 out of 52.
48 out of 52, or is it 48 out of 52?
No, why do they have to do cards? That's just like.
What is it? Give me. What's the probability that we pull a card and it's not a spade? Yeah, it's 3/4 of them.
I said that.
Well, it'd be nice if you guys raised your hands.
The next one is 1/2.
Good. The probability that we pull a red card is 1/2 of them. What's the probability that we pull specifically the 8 of hearts? 1 out of 52. Beautiful. What's the probability that we pull a face card?
12.
12 over 52, which reduces to? Any ideas?
6 over 26.
Keep going.
3 over 13.
Good. 3 over 13. Now, look at that. That's representing there are 3 face cards for every suit. Yeah, I know. All right. Now, We're going to talk theoretical versus experimental probability. We're going to go back to our idea of flipping a coin. When flipping a two-sided coin, what are the odds that it lands on tails? So the probability that we flip tails, in theory, is what? Beautiful. Okay, so 1/2 is about what percent of the time? So now, I'm going to do an experiment where I flip a coin 20 times, or I'm going to flip 20 different coins, actually. We are going to record how many of those times it lands on tails. So I've got my little virtual coin flipper here. It's going to flip 20 coins. Here we go. We're going to count them up. Oh, there's a lot of tails. Okay. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Ooh, that was a lot. So that was 15 tails. Everybody following?
Yeah.
Okay, now let's find the experimental probability of our coin landing on tails. How many times did we flip that coin?
20.
So 15 out of 20. What does that reduce to? Which is about what percent? Okay, what do we notice? Are those two values here, are they the same? Nah, pretty far off, right? Okay, now think about this. They're far off. What do we think is going to happen if we flip more times? What if we flip 100 times? What if we flip 1,000 times? What's going to happen to those percentages?
They're gonna get closer.
They're going to get closer together. So we're going to say the more trials you do, the closer experimental probability will get to theoretical, if I can write. Okay, can we try it really quickly? I'm going to try it. Instead of flipping these 20 coins, let's go back. I'm going to go to its highest setting. I think it goes all the way to 200 if I'm lucky.
We're going to have to count 200 coins.
Nah, don't worry. All right, I'm going to flip my 200 coins. Oh, there's all the coins. 94 of them ended up being reversed, so let's go ahead and check.
Wait, so if you flip infinite coins, then you have infinite most out.
So I upped my number of coins to the most that it would go. It only goes up to 200. Let's calculate what percentage that is. If it's 94 out of 200, I'm going to do 94 divided by 200. I'm going to get 0.47, which is 47%. Much closer to my experimental value, right? Right. Any questions on that? Okay. I got 2 more problems and then we're done. So stick with me for 2 more, please. After receiving complaints, a skateboard manufacturer inspects 1,000 skateboards at random. The manufacturer finds no defects in 992 skateboards. I want to know what's the probability that a skateboard selected at random has no defects. So we're going to say the probability of no defects. How many total skateboards are there?
1,000.
How many of them have no defects?
992.
So in order to find this probability as a percent, I'm going to do 992 divided by 1,000. I'm going to get 0.992. And then how do I write this as a percent?
99%.
I move that decimal twice to get 99.2%. 0.8% are defective, correct. Okay, one more. So, probability is not just used for this kind of stuff. Probability can also help us make predictions. Okay? So, for example, if I have 500 randomly selected households in my town and I survey them and I ask them if they have a dog, out of the 500 households, 197 responded that they do have a dog. So that's going to give us kind of like a theoretical probability for our entire town. Our entire town has 24,800 households. I don't know if anybody really wants to go around to 24,800 households and ask them if they have a dog. So instead, we're going to use our kind of like data that we collected in order to help us make this prediction. The way that we're going to do that is with proportions. I'm okay.
How to what?
So, the first part of my proportion is going to be to set up the experiment that they ran. So they collected a small sample size. 197 out of 500 households had dogs. That's the entire left side here, okay? People that have a dog versus the people that were surveyed. Now, we don't know how many people have dogs in our town, but we do know how many total people are in my town. 24,800. How do we solve this?
Put an X at the top and then cross multiply.
We're cross multiplying 500x equals big number 4,885,600. We're going to divide by 500 to get x equals 9,771.2. I'm talking households here. How many households are likely to have a dog? Can I have 0.2 of a household?
No.
So what should I round to?
Down.
Down, up, round, down.
But that also would be accurate. As accurate as going around. You gotta go around.
Yes, yep, not as accurate as actually going around, but it's a good prediction. Any questions?